Summer concerts, pool parties, chill nights under the stars. We're stocking up our closet so you're ready to look your best for all of it. At Plato's Closet in West Ashley and North Charleston, we're buying all things summer. So bring in your tees, tote bags, sandals, sunglasses, and more. We pay cash on the spot for gently loved name brand looks. Plato's Closet is the go-to destination for trend-forward teens and young adults who support local and shop sustainable. Visit Plato's Closet today. Plato's Closet, located in West Ashley on Sam Rittenberg Boulevard and North Charleston on Rivers Avenue.
Ready to level up your career? Text DISH to 44043 now to dive into a world of exciting technician opportunities at DISH. From cutting-edge technology to a supportive work environment, DISH offers the perfect platform for your success. Connect with us today to discover how you can be part of a dynamic team driving innovation. Connect today and join the DISH family, where innovation meets opportunity. Text DISH to 44043 to kickstart your journey towards a rewarding career.
I'm Sophia.
And I'm Gabriel.
And this is a Breaking Math Problem episode. Before we go into exactly what it is, we're just going to do our plugs really quick. At Patreon, you can support us monthly. It really helps us out. If you pay just $1 or more, you can have the outlines and you can have the episodes with no ads. And if you pay $22.46, you can get the tensor poster with tensor calculus stuff on it. It has some cool diagrams. Everything looks kind of sci-fi. And tensors are used in general relativity. If you just want to buy the poster itself, it's $19.65, which is $15.15 plus $4.50 shipping and handling at facebook.com/breakingmathpodcast. Just click on shop. You can also find updates about the show there. We're on Twitter at Breaking Math Pod. Our website is breakingmathpodcast.app. Updates coming soon. If you want to email us ideas, comments, questions, or corrections, you can email us at breakingmathpodcast@gmail.com.
We also have a sister podcast we would like to promote on this show called the Touring Rabbit Holes Podcast, named after Alan Turing. You can find that at youtube.com/Touring Rabbit Holes Podcast. We need to stop naming things podcast. That's a given. The show is starring a guest who's on the Breaking Math Podcast with some frequency, named Dr. Alan Alanese, and myself actually, and we talk about physics and math as well from his perspective and his history, which is it's a cool show.
So the thing that started us onto this is we've been talking about circles and continuities for like the last few weeks and whatever. But Gabriel, you wanted to just talk about the Socratic seminars again, and like how they led to the question for this episode, which is a kind of nebulous question. How many angles are there in a circle? Do you want to go ahead and explain that?
Absolutely. So this is actually a pivotal moment in both my understanding of mathematics, but also my teaching philosophy. I had mentioned this in the previous episode, so if you listen to that one, then you're a little bit familiar already. I'm going to go into a little bit more detail now. I'm excited to discuss this question specifically because it came from a very formative time in my life as a math teacher. As you may recall from our previous episode, I was once a math teacher at a small charter school here in Albuquerque, New Mexico called Cottonwood Classical Preparatory School. This school had a requirement as part of its charter that every single subject would participate in something called Socratic seminars. That is, student-led, open-ended discussions in all the classes that are about a philosophical topic or an idea, and it's not graded on correctness so much as it is on participation. Now, we even had them in math and science classes, and I thought that was quite neat.
I find that interesting too, because a lot of times math is presented as the set of rules they have to follow. Like, you have the quadratic formula that you memorize and all this other honestly, debilitating math practice, and I find that very interesting.
You're exactly right. Anytime I think of math in any typical classroom, it's exactly what you said. You've got a math textbook with problems, and you solve it with the formula the teacher gives you.
Which is like paint by numbers to art, which is not an example I thought of.
Exactly. So in a math class, every couple of weeks or so, we would move all the desks aside and set up all the chairs so they're facing each other, and there would be a discussion just based on, a philosophical idea. I thought this was brilliant, and I specifically wanted to mention this experience on this podcast because I'd love it for this practice to be adopted throughout. In fact, if anybody has questions about it, feel free to send them to me, at breakingmathpodcast@gmail.com, and I'll tell you a bit more about this practice of Socratic seminars. Now, during one Socratic seminar in this math class, we were discussing infinity. I don't quite recall what the specific question was that started the conversation, but at one point, the question was asked, do circles have 0 angles? Or do they have an infinite amount of angles? The students were allowed to think about it and then discuss it following, some basic rules of discussion. I found this question fascinating. And again, I don't even remember where it came from. It was brought up in the natural flow of this conversation. Now, I do want to specify that by angles, we can also call it points as well. Of course, a point would be where 2 lines intersect at any, degree.
Well, and I think what, specifically, definitely what you mean is because an angle is between 3 points, or kind of like the intersection between 2 lines, right?
Correct.
And a point is just where they intersect. So you could see every point on the circle as having an angle because there's a line going into and out of that.
Yeah. Now, what was cool is again, this conversation was with middle school students, and we're not grading for mathematical rigor or even necessarily correctness. We're just grading on participation. The discussion followed like so. You can start off with a single point, and then you can add another point with which you can make a line between the 2 points. You can add a third point, and you would get a triangle. A fourth point would create a square, and you can keep adding points in this general shape. And again, I realize we discussed this on previous episodes, but it's worth bringing up again. You can, add 8 points and create an octagon. Essentially, you can add n points and create an n-sided shape. That essentially approaches a circle. So the argument could be made that a circle has infinite angles, infinite points.
Yeah, and of course, every point can be said to have an angle, and we also had the discussion last time on the episode. We were going to go into more detail, and you said you had it in the Socratic seminar as well.
Yes,
the idea of an infinitely large circle being a straight line.
Yes. So again, just as long as students are talking about infinity and ways to I don't want to say measure it, but grasp it, at least conversationally. The students had said, so as you start with a circle, and if you increase the radii, it appears to come apart, so to speak. Well, if you stand on the earth, it may appear flat. We know that it's curved, but it certainly appears flat. So from a given vantage point, if you increase the size of a circle, in the process of increasing the size, perhaps it could appear to get flat. The question was asked, if you increase a circle so that the radius is an infinite length, do you have a flat line or not? Discuss. And again, in the spirit of a Socratic seminar, we're not necessarily concerned, at least right away, with rigorous mathematical definitions, but more or less the process of how you get there. And I thought that was a brilliant, brilliant question. It took me a very long time to arrive at what I believe is the right answer. But I say this more as an approach for learning, and I hope that some other teachers might adopt Socratic seminars even in math classes.
Yeah, I mean, it's definitely a good thing to encourage this kind of open-ended discussion, and it also keeps the teacher on their toes, and as a teacher should be. If a teacher of yours, a professor of yours, anyone like that, if they can't deal with you asking questions or you pointing out things that you think are wrong, then they are not good at their job. Just simple as that.
Yes.
And most of the people in the audience, most of their teachers are probably bad teachers, in my experience, and it's because of this fear. So in that spirit. But also in that spirit, and also the spirit of Breaking Math Problem episode rigor, we're going to go into these questions.
Now, without further ado, we will attempt to answer both of these questions with a bit more rigor than what happened during the Socratic seminar.
So we talked about in the last episode that there's this cardinality, meaning this amount called Aleph1, and it's the amount of real numbers that there are, right? 1.3, pi, anything that you could think of that's a number. Mm-hmm. The number of the cardinality of those is Aleph1.
Correct.
And Aleph1 is uncountable, right?
Mm-hmm.
Meaning that Aleph0 is all the natural numbers or all the squares. Go back to last episode if you want more information on that. Mm-hmm. But you cannot put all the points in a plane or a line or a cube in order. You will leave some out every time.
Yes.
In fact, you'll leave out literally 99.9999 infinite number of 9% of them, basically only 1 over infinity of the points is what you'll get if you have a countable number of points.
Yes, and again, what you're saying is, so if you draw a straight line, there are an uncountable amount of points in that line, and you can also take that straight line and bend it into a perfect circle mathematically. And the same thing would apply because a perfect circle can be made simply by a straight line.
Yeah, and because the line segment also has the same number of points as the whole real line, right?
Yes, so that should be in of itself sufficient to mathematically prove that a circle has an uncountable amount of points.
Yeah, because for every point in a circle, there's a point on some line, and we could stretch that line out from negative infinity to infinity in a rigorous way using a inverse sigmoid function. Like arctangent or various means.
Yes.
And yeah.
We will now discuss a little bit about the differences and similarities between an angle and a point on the circumference of a circle.
So obviously the points on the circumference of the circle are just the points that make up that circumference, right?
Correct.
And there's Aleph-1 of those.
Yes.
But so you could say that each point on the circle, right, if we zoom in far enough, it's going to have some angle, right? Because let's go back to the triangle square thing, right?
Yes.
The triangle has angles of 60 degrees if they're all equal, right?
Yes, an equilateral triangle, correct.
Yeah, and if it's a four-sided figure, then everything has 90 degrees.
Assuming that, unless you've got a rhombus, but...
Oh yeah, but I'm just saying like equidistant points, so that like all points are equidistant from each other and all equidistant from some center point, and that's how we could define things that approach a circle without using the concept of a circle.
Yes.
And if you keep moving, you notice that these numbers will get bigger and bigger, but there is something that they are approaching, and that is 180 degrees, which is just a straight line, 2 right angles.
Correct.
And so you might think like, oh, how can this be? How can we go all the way to infinity? And the thing is, all we have to do is use the definition of a circle, which is continuous itself, right?
Yes.
And this was actually proven by Euclid like 2,500 years ago or whatever. So let's imagine that you have a circle, right? Imagine a circle in front of you, and there's a line resting on top of the circle, right?
Yes.
So it looks like a wheel rolling on like a drawing of a road or something like that.
Sure, absolutely. Just so any circle that comes into contact with a straight line, and
at exactly one point.
Yes.
So there's no chords within the line, anything like that.
Okay, so a perfectly straight line touching a perfectly round circle, and it doesn't go through it; it touches it at one point.
Yeah, and touching it at one point means it's tangent to that line.
Correct.
Now let's say we draw a line from the center of the circle to the point that the line meets the circle, right? That one point that it touches.
Yes.
That will be the radius of the circle, right?
Correct.
And that's just by the definition of a radius. A circle is a point and a radius.
Yes.
And the radius touches the edge from the center. So what is the angle between the radius and the tangent line?
So just those two is, it's two 90-degree angles or a single 180-degree angle.
Yeah, and 180 degrees total with like 90 degrees on each side, right?
Correct.
So it like meets it at a perfect L.
Perfect perpendicular. Yeah, this is like, high school or even, elementary geometry.
What's interesting, though, is that it's something that needs to be proven within Euclid's system. There's not enough. It's something that we actually have to prove rigorously. And we're going to do that now. But instead of imagining this abstract circle, because we're going to get a little bit complicated, we're going to make it a little bit simpler by making it physical for you. So imagine you have a plate, right?
Yes.
On a table. It's a round plate. And you get a ruler and you touch it to the edge of the plate. So it just like... So the line on the edge of the ruler is tangent to the circle that's on the edge of the plate, right? So let's suppose though that if I draw a line from like the center of the circle to the ruler and then draw the line along the ruler, it's going to be a 90-degree angle. That's what we claim, right?
Correct.
So we're going to do a proof by contradiction, and we're going to assume the opposite.
Okay. We're
going to assume that it is not a 90-degree angle. So we're going to assume that there's some point. Let's just say that it's to the right on the ruler. So like you just go down the ruler a little bit outside of where it's touching the plate. And at this point, let's suppose that is the 90-degree angle.
Yes.
And if it were on the left, you just have to flip the scene around, do it in a mirror. So that means that if we made a triangle going from the center of the plate to the point that we're claiming it's a right angle, right, on the ruler.
Yes.
Let's just say we mark that with a red dot. Okay. So to the red dot and to the point where the plate meets the circle and back, it would have a 90-degree. We're saying that it would have a 90-degree angle at that dot, right? At that on the ruler.
Okay.
So How many degrees are there in a triangle, in the interior angles?
180.
Yeah, and since we already used up 90 of those, the two angles that remain, which is again the angle at the center of the circle, right?
Mm-hmm.
And the angle where the ruler touches the radius, we're saying that both of those must be less than 90 degrees, right?
Correct.
Because you have to split 90 degrees between two things.
Mm-hmm.
So in triangles, like one fact about triangles that we don't want to prove here, you could find plenty of wonderful proofs online, is that in a triangle, the angle that is the largest, the opposite side is also the longest of the sides.
Mm-hmm.
So does that make sense?
Yes, it does. Absolutely.
And so since it's the greatest angle, the opposite side is the line on our triangle that goes from the center of the circle, of the plate to the ruler, right?
Mm-hmm.
And we're saying that distance must be longer than the distance from the center of the circle to the point on a ruler outside of the circle.
Mm-hmm.
But since the distance to that point, right, the point, that red point, is longer than the radius because it contains the radius, right?
Mm-hmm.
It must be longer than the other piece.
Mm-hmm.
So we have a contradiction there.
I see. And that must mean that we've proven out what we've set to prove.
Yeah, exactly. And so it's kind of weird though, right? Because what we've proven here is that at every point in the circle it seems to be a flat line. It seems to not be different than a flat line.
Correct.
Which seems a little bit weird. One might have the question, where did the angle go? How do we measure that?
Mm-hmm. However, essentially what we're saying is that for the purpose of a circle, every point on the circle is an angle.
And you could say it's an angle because you can imagine first that you draw 2 points next to the circle, right?
Mm-hmm.
And then you draw the angle and then you get the points closer and closer. So there really is this infinitesimal calculus aspect to a lot of Euclid's proofs, especially the ones dealing with circles where they kind of bypass that with clever stuff.
Yes.
But
so what we're showing then is that this proof shows that earlier we accepted that a circle has an infinite amount of points. Again, through this more formal, rigorous proof, a circle also has an infinite amount of angles.
And all of those angles are a straight line.
Yes.
Which is weird.
It is weird.
So why is a circle not a straight line?
So now, so I love your transition. So since every angle on a circle is like a straight line, why is a circle not a straight line? This is the other part of the question from the Socratic seminar that was brought up. Or rather, it's similar to it, and I think it's a wonderful lead-in to that second question. That question was, if you have a circle from a given point, from a given vantage point, and if you continuously increase the circle all the way to infinity, granted, that's not actually possible, but if you were to increase the radius of a circle to infinity, would the circle be a straight line?
And we could examine that a little bit by looking at the idea of infinitesimal change as you go along paths. So let's imagine real quick that you're on a roller coaster, right?
Yes.
If you've been on a roller coaster or even in a car, you notice that when you take curves and stuff, you feel centrifugal force, right?
Correct.
Believe it or not, the centrifugal force is related to a concept called curvature, which allows us to discuss what we're talking about.
Yes.
So let's do a quick review on velocity and acceleration. Gabriel, what does it mean to say that velocity is the time derivative of position?
So a derivative is a measure of change, essentially. So if velocity is the time derivative of position, it is the change in position over time, and it happens in infinitesimal increments.
Yeah, and I think it's kind of cool because if you keep going with this, and we've talked about this many times, but it bears repeating because it's a new episode, the acceleration is a time derivative of the velocity.
Correct.
So, and that means it's measured in like units of distance per time. So like an acceleration of 1 meter per second would mean that after 1 second is going 1 meter per second. After 2 seconds is going 2 meters per second, and so on. Mm-hmm. So now that we got that out of the way, let's talk about arc length parametrization. So parametrization is you put in a variable like time, right? Mm-hmm. And you go along a path and it squiggles out a path. You have like some vector or some point generated at every point. So for a circle, it might take 2 pi of our units, depending on how we write it, and it would go along in a circle generating an x and a y coordinate at every point for time, right? Mm-hmm. But the arc length parameterization is assuming that we draw a curve in midair. Imagine a roller coaster where you're going the same speed the entire time.
Right.
Which that would be the arc length parameterization of a curve. And we can use that to talk about curvature. So yeah, so arc length parameterization, let's just say we call that gamma of s being the distance.
Okay.
So if we follow the curve from gamma 0 to gamma s, we'll have traveled how many units along that curve?
S units along that curve.
So now if we take the derivative over s, it's kind of like taking the derivative over time of a particle moving at a constant speed along that path, right?
Mm-hmm.
So that is like the velocity, and it's the first derivative of the arc length parameterization position.
Mm-hmm.
So if we call that gamma, the tangent vector, which is also the velocity, will be called t of s, which is gamma prime of s, prime meaning derivative, and it's something that you need to do with context. Yeah, so now the derivative of the velocity is acceleration, right?
Yes.
If we take the second derivative of our arc length parameterization, that is the velocity, that is the acceleration that we would feel along that point. So if we're basically this would be like if we were in space going along this path, how our stomachs would turn basically, where gravity would feel like it's going.
Mm-hmm.
And it's just the magnitude, and the curvature is the magnitude of that acceleration. Because remember, acceleration, like let's say we're doing a circle, right? Mm-hmm. The acceleration will be pointing towards the center. It's the same reason why the moon orbits the Earth. The Earth is pulling on the moon and the moon is moving sideways.
Yes.
So the magnitude of the acceleration is of a arc length parameterization is the curvature.
Mm-hmm.
And what's cool about the curvature is it's inversely proportional to the radius. If you're drawing a circle, then it's like that, right? It's inversely proportional to the radius. So if our radius is 3, our curvature is 1/3. If our radius is infinity, our curvature is what?
0.
Yeah, so in that way, we could imagine a straight line being a circle, and then, because one of my problems sometimes with defining a straight line as a circle, depending on what system, is in Euclidean geometry, it doesn't seem to make much sense, right?
Correct.
Because the radius would have to be infinity plus like 3 feet away, which doesn't make much sense.
Yes.
But with this thing, with the parameterization, you can basically freeze the velocity in time, and a circle in this system is a straight line if it's infinite.
This is so interesting. This is so interesting. So when we're talking about infinitesimals, like in this problem, a circle is necessarily a straight line at a certain point.
Yeah, it's the system that we work in, because we really have to be careful with that as mathematicians, because I mean, a famous example is naive set theory was used in the late 1800s, and then somebody said, I can't remember who it was, what if you had the set of all sets that don't contain themselves, right?
Yes.
Would that set contain itself?
Oh, wow. There you go.
The answer is both yes and no. So that means that naive set theory is bad. So if you're working in Euclidean geometry, a straight line cannot be a circle. If you're working on the surface of a sphere, every straight line is a circle.
Yes. Wow. Goodness. That's a head spinner.
Yeah, right.
Yes. Yes.
And this actually applies for every continuous function. So anything that doesn't jump or like change. So like if I change directions infinitely abruptly, first of all, I would probably disintegrate because my acceleration would be infinite and I would turn into a cloud of light. But if I approach that is like that would be like a curvature of infinity at that point. Mm-hmm. And that's really the only place the angles exist on a path, is where the curvature changes abruptly. Because those are the only angles that are not 180 degrees. Mm-hmm. So I just think that's kind of fascinating that just infinitesimal calculus has given us a way to talk about the tangent of pretty much anything. Thank you, Newton and Leibniz.
Yes, that's fascinating. Now, earlier you were saying, before we got into the physics element, you were saying that the curvature is inversely proportional to the radius.
Yeah, and we can actually show that with the physics. So the centrifugal force that we feel when we're going around a circle is equal to the square of the angular velocity, which is basically radians of a radian is the angle that one radius subtends. Mm-hmm. Is radians over time, right?
Yes.
So the acceleration that you feel going around a circle is omega, which is angular velocity squared times r.
Yes.
Let's imagine that we are traveling at speed 1 around a circle, right?
Yes.
And can you explain what speed 1 means?
Sure. Again, speed, or rather velocity, is the derivative of position. So it's the change in position over time.
Yeah, so if we're going at speed 1, it means we're going 1 unit of distance per 1 unit of time, or like 10 units of distance per 10 units of time. They're equal, right?
Yes.
So let's say we have a circle of radius of r, right? R distance units.
Okay.
What will the circumference of that circle be?
If it's r, the circumference would be 2 pi r.
All right, so since we're going 2 pi radians, right, which
Yes.
is a full circle,
Yep.
in a full circle.
Yep.
In 2 pi r time, that means that we're going 1 over r radians per second, which means that omega is 1 over r. And so acceleration, we already said, is omega squared r, right?
Yes.
So omega is 1 over r. So what's 1 over r squared times r?
1 over r.
Yep. And since that means acceleration is equal to 1 over r. And so since acceleration is kind of what our curvature is, or at least, the magnitude of acceleration is what our curvature is.
Yes.
That means that curvature is inversely proportional to r using this physical argument.
Yes. So when we explore creating a circle through acceleration, or rather moving at a constant speed in a circle, that is a form of acceleration. And we have shown that all continuous functions have an angle, quote unquote, of 180 degrees. And an angle is a way of measuring an abrupt change or relation. The reason why is because the tangent can be calculated using calculus. Now, with respect to circles and polygons, we said earlier, we talked about creating a shape that approximates a circle by continuing to add angles that are the same distance apart.
Yeah, which was also just quick. Archimedes of Syracuse used that to calculate his values for pi.
Yes, where he made a both on the inside of a circle and on the outside of a circle. He made the outside of a circle. He kept adding angles, and the same as the inside. So they got closer and closer to approximating each other's shape.
And then he took the average of those two.
Yes,
and he got really close. Like he got like 3 digits, I believe.
Yes, exactly. So he kept adding angles to a polygon, and they ended up at a circle.
And the proof in Euclid that also uses this, by the way, that if you keep adding angles to the circle, I think it's a proof on there's a few proofs that use that, like the proof that the volume of a cylinder is equal to the area of the circle times the height uses this, because you have like basically a triangular prism, and you keep adding segments to it, and you inscribe and circumscribe it. And the thing that you do with that is that when it goes to infinity, you show that it can't be more or less than something.
So through discussing derivatives and acceleration in physics, we have a roundabout way of discussing whether a circle with an infinite radius is in fact a straight line, and how this is a different way of answering that question. So the answer would be it's made of infinite straight lines.
Either it's made of infinite straight lines, or it cannot be defined as in traditional Euclidean stuff, or it is a line because it's parametrized as an infinite circle. Like you can imagine, like when you get those audio bugs where you just go like,
yes,
and it's kind of like that basically.
Yes,
we're like when you hold I'm not sure if you did this as a kid, but like if you ever had one of those fans that goes back and forth, if you hold it in place, it clicks and squeaks, and probably it's not good for the fan. Yes, we're doing that for the circle.
Pretty much, yes. And the other thing is, without getting into the rigorous mathematics, but just talking about definitions, I prefer to say that it's a meaningless idea to discuss a circle with a radius of infinity. I prefer to, I don't want to say, as my cop-out, as it were, but I prefer to say that question in of itself is meaningless.
And I think that my philosophical view on it is slightly similar and slightly different. My view is that it makes sense only to talk about the side of the circle that you can see if it's a straight line. The other side of the circle is meaningless to talk about. Yeah,
absolutely. So again, when we talk about infinitesimals, as soon as you bring infinity to the party, things get weird.
Oh yeah, and honestly, like the outline of like Daffy Duck could be considered a straight line if you made it big enough.
Yes, exactly.
So it is weird.
So I was thrilled to do this problems episode because we both get into some rigorous mathematics, but we also, and I honestly think more importantly, arguably, I introduced the idea of doing an open-ended Socratic seminar discussion with kids in middle school and see where the conversation goes.
Yeah, ideas are born of discussion. And if you teach your students how to respond to new information or contradictory information by processing it in front of them, you can do them a great service. It's critical thinking. It's all this good stuff. So, Gabriel's suggestion is amazing.
Thank you. And it wasn't my idea, but I got to witness it.
Gabriel came up with this idea. Socrates was a myth.
Oh, gosh. All right. Until next time.
I'm Sophia.
And I'm Gabriel.
And this has been a Breaking Math Problem episode. Email us at breakingmathpodcast@gmail.com and contribute to our Patreon at patreon.com/breakingmath.
With everything you have on your plate, earning your degree online seems impossible. But at Grand Canyon University, we specialize in helping you fit a master's degree in education into your busy day. Your graduation team, led by your own GCU counselor, provides you with the personal support you need to succeed. Achieve your goals with a plan and team behind you. Find your purpose at Grand Canyon University. Visit gcu.edu.